Welcome back to Very Ordinary Differential Equations. In this lecture, we extend our technique of variation of parameters to second-order equations. Well, let's refresh how first-order variation of parameters works. Suppose we have a first-order differential equation of the form y prime plus a function of x times y equals another function of x. And let's assume I have a y sub 1 which solves the homogeneous equation. So y1 prime plus p of x y1 equals 0. I suppose that y sub p is some unknown function u times y1. I'm also going to compute yp prime via the product rule. Then I'm going to assume that yp actually solves the differential equation we began with and substitute in yp prime that we just computed with the product rule. And it will work out to be this. However, I now have this expression here involving only y1. So, having assumed that a solution yp is of the form uy1 and thrown it into our differential equation, we have this. But y1 was a solution to the homogeneous equation. So if I group together the terms with u, we actually find y1 prime plus py1, which is 0 because y1 is a solution to the homogeneous complementary equation. So we can drop that term and we just get u prime y1 equals f. In other words, u prime is f over y1. F was the forcing function we began with, and y1 is a solution to the complementary equation that by assumption we already know. So now I just have to integrate that to find u. So what we're going to do, we're going to take this technique and extend it to second order equations. So suppose we have a general second order linear equation, some function of xy double prime, some function of xy prime, some function of x times y equals some other function of x. Also, suppose y1 and y2 are a fundamental set of solutions to the complementary equation. So we set a particular solution to be one unknown function times y1 plus another unknown function times y2 and proceed more or less the same way. So yp prime, by applying the product rule to both of the terms, can be computed as this. u1 prime times y1 plus u1 times y1 prime plus u2 prime y2 plus u2 y2 prime. We're also going to make a simplifying assumption. Let's just pretend that u1 prime y1 plus u2 prime y2 happens to be equal to 0. Well then, u1 prime y1 plus u2 prime y2 will be 0, so only these two terms remain. So then yp prime can actually be written in the simpler way, u1 y1 prime plus u2 y2 prime. So with some simplifying assumptions, yp prime can be written like this. Well then, I'm going to compute a second derivative, again using the product rule. So I take yp prime and yp double prime and I throw it into the differential equation under the assumption that it's going to be a solution. It's a little messy at first, but here is p0 times yp double prime plus p1 times yp prime plus p2 times yp equals capital F. After we rearrange a bunch of terms, okay, we're factoring out a u1 from a bunch of terms and a u2 from a bunch of terms, leaving behind just this extra stuff. But now notice what's been left behind after factoring a u1. p0 y1 double prime, p1 y prime, p2 y1. And what's multiplying u2? p0 y2 double prime, p1 y2 prime, p2 y2. But y1 and y2, by assumption, were solutions to the complementary equation. So both of those terms are 0, and all we have is p0 times u1 prime y1 prime plus u2 prime y2 prime equals f. So where are we right now? We're looking for two functions u1 and u2, which simultaneously solve u1 prime y1 plus u2 prime y2 is 0. We made this assumption to simplify our work earlier, so this needs to be true. But also, u1 prime y1 prime plus u2 prime y2 prime needs to be f over p sub 0. If we multiply the first equation by y2 prime and the second equation by y2, So this equation now has a y2 prime here, and this has a y2, so these two terms can now match up, and I can combine these equations in a creative way. Okay, so here's my first equation multiplied by y2 prime. Here's my second equation multiplied by y2. I can take the difference of these two equations. If I take these two equations we've just generated, and I subtract the top one from the bottom one, well, these two terms will cancel out. Both of these have a shared factor of u1 prime, leaving behind y1 prime y2 minus y1 y2 prime. And here I'll just have this minus 0. Now recall that y1 and y2 is a fundamental set of solutions, meaning that they are independent of one another. They're linearly independent, so this Wronskian y1 y2 prime minus y1 prime y2 is never 0. And that's exactly what we have here, up to a minus sign. So this is not 0. If it's not 0, we can divide both sides by it. And u1 prime must be f y2 over p naught times the quantity y1 prime y2 minus y1 y2 prime. So u1 was an unknown function, and it has to satisfy this. So u1, whatever it was, must satisfy its derivative is this expression here, and everything on the right is something that by assumption we know. Capital F and P naught were from the original differential equation, and y1 and y2 were a fundamental set of solutions to the complementary equation. So we go back to the original system. Here, this is what we needed to be true. What we did before was multiply the top by y2 prime and the bottom by y2. And that's how we got this expression up here. But now we're going to multiply the top by y1 prime and the bottom by y1 and take a difference. Very similar work is going to allow us to solve for u2 prime. Well, if we go through all of that work, here's what we had before for u1 prime. And if we go through all the work again, we're going to get this expression for u2 prime. Integrating both of those, hopefully doable, can be used to recover the functions u1 and u2. Okay, and again, any constant of integration is fine. We're not interested in finding all functions u1 and u2 that solve this. We just need an example of a function u1 and u2 that solves this. And once you find a u1 and you find a u2 by integrating these, picking whatever constant of integration you want, well then you can go back and express your solution y sub p. It's just u1 y1 plus u2 y2. In which case the general solution can now be written as a linear combination of your fundamental set plus the particular solution you just found. A lot of times this is then factored. Okay? If yp is u1 y1 plus u2 y2, well, yp has a u1 y1, so I can combine that here with this term like that, and the u2 y2 and yp can be combined with the c2 y2 right here. I tend to write it in this form here, but it is really common to see it written in that form down there as well. Let's take this new technique and apply it to an example. Find all possible solutions to y double prime plus 6y prime plus 8y equals e to the minus x. Well, first let's find a fundamental set of solutions. Variation of parameters assumes we've already done that. Well, it's a second order linear equation with constant coefficients. So we construct the complementary polynomial r squared plus 6r plus 8. It has two roots, -2 and -4. Therefore, a fundamental set of solutions is given by e to the minus 2x, e to the minus 4x. The forcing function isn't in the fundamental set of solutions, so we could use the method of undetermined coefficients from a few videos ago. We would set y sub p to be an unknown constant times e to the minus x and just solve from there. But we're going to use our new technique just to get a little more used to it. So we have a fundamental set of solutions, e to the minus 2x, e to the minus 4x. So now what we have to do is find an unknown function u1 and another unknown function u2, which are given by these expressions as we solved for before. So we have to compute fy2 over p naught y1 prime y2 minus y1 y2 prime, and similarly for the other expression, and then integrate. So let's just see what we've got. P naught is whatever is multiplying y double prime in our original differential equation. That's just 1. F of x is our forcing function, e to the minus x. We have to pick an order for which of these is y1 and which of them is y2. I'm just going to let y1 be first and y2 be second, in which case I can now compute y1 prime, y2 prime, etc. So here is our expression. u1 prime is given by all of this. With our choice of which is y2 and which is y1 and all of the various derivatives, and p naught is 1 and capital F is e to the minus x, it all works out to be this. So we get e to the minus 5x in the numerator and 2e to the minus 6x in the denominator. Overall, 1/2 e to the x is u1 prime. Not actually very tough to integrate. u1 is 1/2 e to the x. Okay, so we found u1. Now we're going to go through all the same work to find u2. Well, here's the expression for u2 prime. Well, with all of our choices for y1 and y2 and f and p naught, etc., here's everything that pops out. We get e to the minus 3x over negative 2 e to the minus 6x. So we have negative 1/2 e to the 3x, which again is not very difficult to integrate. It's just negative 1/6 e to the 3x. And remember, you can make any choice for your constant of integration, so I'm picking 0. Then our general solution is given by c1 plus u1 times y1 plus c2 plus u2 times y2. C1 and C2 are arbitrary constants, Y1 and Y2 were our fundamental set of solutions, and we just solved for U1 and U2. So C1 plus 1/2 e to the x times e to the minus 2x plus C2 minus 1/6 e to the 3x times e to the minus 4x. Alternately, if you simply computed yp as u1 y1 plus u2 y2, and then wrote it with this form, you would end up with c1 e to the minus 2x plus c2 e to the minus 4x plus 1/3 e to the minus x. It's worth noting all you would do is take this expression here and distribute everything. You would end up at exactly the same place. c1 e to the minus 2x, there. c2 e to the minus 4x, there. Here you're going to get 1/2 e to the minus x. Here you're going to get negative 1/6 e to the minus x, which combine to be 1/3 e to the minus x. So they are exactly the same result. As a second example, let's find a particular solution to this differential equation, given that x and e to the x both solve the complementary equation. Well, given that both of them solve the complementary equation, we have a fundamental set of solutions. So let's set y1 to be x and y2 to be e to the x. Also, p naught of x is whatever is multiplying y double prime, that's x minus 1, and capital F of x is the forcing function, x minus 1 cubed e to the 3x. Then we just have to compute two things. First, u1 prime has to satisfy this expression right here. But f was given to us, it's here. y2 is e to the x. p naught was given to us. y1 is x, and so we can compute all of these terms. u2 prime is also given by a very similar expression. So u1 prime was given by this expression here, and once we make all of our relevant computations and plug in, we end up with this. Okay, so we have x minus 1 cubed e to the 3x over x minus 1 e to the x minus x e to the x. Observe down there in the denominator, if you factor an e to the x out of this term right here, you're left with a 1 minus x. A lot of stuff cancels here. X minus 1 cubed over x minus 1. I can cancel one of those out. Also, it's not immediately obvious, but x minus 1 squared is the same thing as 1 minus x squared. So once I cancel this out and I have squared and I remove that, I'm going to replace that with 1 minus x squared, cancel that with that down there, and that leaves me with exactly what we have at the bottom. 1 minus x times e to the 2x, once I simplify e to the 3x over e to the x, gives me e to the 2x. So having found that u1 prime must be 1 minus x times e to the 2x, we just have to integrate. Okay, using a computer algebra system or just integration by parts, you'll get u1 is 1/4 e to the 2x times the quantity 3 minus 2x. Similarly, we now have to compute u2 prime according to this formula, but again, f was known, p naught was known, y1, y2, their derivatives, we compute them, and we end up with this expression here. Okay, this simplifies pretty directly. I cancel this x minus 1 with one of those. If I factor an e to the x out, I get an x minus 1 that I also cancel, and then I cancel the e minus x I just factored out with one of these to leave e to the 2x up there. So u2 prime is x minus 1 times e to the 2x. Integrating that gives me u2 is 1/4 e to the 2x times 2x minus 3, which happens to be exactly negative u1. So then all we have to do is we set yp is u1 y1 plus u2 y2. Of course, u2 happened to work out in this problem to be negative u1. So I can factor a u1 and just be left with y1 minus y2. u1 was 1/4 e to the 2x times 3 minus 2x. y1 is x, y2 is e to the x, and there it is. So here's y sub p. One particular solution to the differential equation we started with. As a third example, let's solve the initial value problem. The differential equation looks pretty ugly, but we do have some initial values. Also, we're given that e to the 2x and x e to the minus x both solve the complementary equation. Well, if we already have a fundamental set of solutions, we really jump right to finding u1 and u2 using the formulas that we have. We just have to specify from our fundamental set of solutions which one am I calling y sub 1 and which one am I calling y sub 2. Well, here is our formula for u1 prime. F is the forcing function, 3x minus 1 squared e to the 2x. y2 was x e to the minus x. P0 is the coefficient on y double prime, that's 3x minus 1. y1 prime is 2e to the 2x, y2 minus y1, y2 prime. All right, so now it's just a matter of simplifying some things. Well, one thing that simplifies rather nicely is 3x minus 1 squared over 3x minus 1. I can cancel that out from the denominator, leaving just 3x minus 1 in the numerator. Also, e to the 2x times e to the minus x gives me just an e to the x up here. Similarly, if I combine e to the 2x and e to the minus x, e to the 2x and e to the minus x, I get various terms that just have e to the x in them. And also, we've distributed out this 1 minus x here to give us two different terms. Now, the denominator, I can factor an e to the x out. Factoring an e to the x out gives me a 2x minus 1 plus x, so just 3x minus 1. Those cancel, as will the e to the x's. u1 prime is just x, which I can easily integrate as x squared over 2. Okay, we just have to keep doing similar work. Here's our expression for u2 prime. With all of our relevant computations done, it works out to be this, which simplifies down to negative e to the minus x. Well, if that's u2 prime, it's not terribly difficult to see that u2 has to also be negative e to the x. Well, then we can compute our particular solution to be u1 y1 plus u2 y2. Remember that u1 was exactly x squared over 2, and u2 was negative e to the x. So that negative e to the x will cancel this e to the minus x, leaving behind just the minus sign there. So here is our particular solution, y sub p. This means our general solution is of the form c1y1 plus c2y2 plus y sub p. So here we have c1y1 plus c2y2 plus the particular solution we just found. Since we know we're going to be doing an initial value problem, we are going to need to compute a derivative of this. And here it is. Okay, so differentiating term by term. Chain rule just spits out a 2. I need a product rule and a chain rule. It works out to be c2 times 1 minus x. Okay, various product rules here give me x squared e to the 2x or x e to the 2x, and then this derivative is just a nice minus 1. We're now in a position to use our initial conditions, so here was our expression for y. But since y of 0 is 1, if I replace all the x's with 0, these terms all vanish. E to the 0 is 1, so this is just c1. However, when I replace x with 0, I should get y is equal to 1, so we get c1 as 1. From the derivative, we take y prime of 0 as 2. We replace all of our x's with 0, so this vanishes and this vanishes. Okay, but here this becomes a 1. E to the 0 becomes a 1, becomes a 1. But y prime of 0 is 2, so overall we have 2 equals 2c1 plus c2 minus 1. But we already knew that c1 was 1. Okay, and if c1 is 1, we have 2 equals 2 plus c2 minus 1. In other words, c2 is also 1. So if c1 is 1 and c2 is 1, well then we have exactly what y is. E to the 2x plus x e to the minus x plus x squared over 2 e to the 2x minus x. So there is the unique solution to the differential equation subject to the initial values given. Overall, what have we covered? Variation of parameters, frankly speaking, is a very powerful and useful method for finding solutions to second-order linear differential equations. Unlike the method of undetermined coefficients that we spent several videos on earlier, you can always attempt this. Okay? Undetermined coefficients really only worked for specific forms of the forcing function, but variation of parameters, you can always try. Variation of parameters can even be attempted for equations that don't have constant coefficients. All of the videos we did before with polynomial forcing functions, exponential forcing functions, etc., they always had this assumption that the differential equation had constant coefficients. Variation of parameters does not need to make that assumption. Finding a fundamental set of solutions, however, is necessary before you can attempt variation of parameters. And if you have a very complicated differential equation with non-constant coefficients, that itself might be incredibly difficult.